Okay, you're here to learn about force. So remember the routine. When I ask a question, pause the video and think about it. The video you'll learn a lot better if you interact with the video and don't just passively watch it. So think about what is a force. Just think about it for a minute and come back. Okay, so I always start with this, like very simple. Every force is a push or a pull. So let's look at some examples, and I'll give you some examples from the next two labs that we're going to do. Okay, here are three situations from Lab 5. A flat track and a fan cart. A fan cart with a counterweight. So in this case, the fan is going to make the cart accelerate. In this case, we'll put a counterweight to balance the forward force of the fan. And in this situation, we'll tilt the track so that the fan force going up the track will be equal to that part of gravity that's pulling the cart down the track, and they'll be balanced. So this is a balanced situation. This is a balanced situation. This is a situation that's going to accelerate. Okay, so we're talking about forces. Let's identify the forces, all the forces acting in each of these situations. And what we're going to practice to do that is to draw a free body diagram that take the cart out of the situation and show all the forces acting. And in this case, there were three forces acting. There's the fan force. There's the force of gravity on the cart, right? The cart is pushing down on the track. We call that Fg. And I'll just mention that we can calculate that by the mass of the cart times g. That's how we calculate the force of gravity. But that's balanced, right? The cart's not falling. It's not in free fall. So what keeps it from falling is the track pushing up on the cart. And we call that a normal force. Normal. This is an important force that we'll see a lot of. Normal means perpendicular. So if you put a book on a table, or a car on the road, or a person standing on the floor, there's always the surface pushing up perpendicular to the surface, and that we call an Fn, or a normal force. So notice in this situation, we have two forces which are balanced in the y direction, and that means the cart isn't going to move or accelerate in the y direction. And in the x direction, there's an unbalanced force. So what do you think is going to happen? The cart's going to accelerate. And so that leads us to the other important part of what we're going to learn. What is the relationship between force and motion? And that is stated in Newton's second law, which says that the sum of the forces, the vector sum of all forces acting on an object, will be equal to its mass times its acceleration. So this equation is the central relationship. Notice I'm calling it a relationship because it's the relationship, a quantitative relationship, between the net force acting on an object, the mass of the object, and the acceleration. So notice here, in the y direction, the two forces balance, so the sum of the forces in the y direction are 0, and there's no acceleration. In the x direction, because the cart is frictionless and the track is flat, there's an unbalanced single force, the fan force, that will lead to an acceleration. So that shows us that when we do these problems, when we do force problems, it's essential, not just important, essential, that we split this equation into two equations in two directions, because as you can see in this problem, there's two distinct different situations in the y direction and in the x direction. And that's very similar to what we saw with projectile motion. Okay, now let's talk about the forces. So, is the force of gravity a push or a pull? Is the normal force a push or a pull? And is the fan a push or fan force a push or a pull? So answer that question. And the answer is gravity's a pull. The Earth, without touching things, that's interesting, we'll talk more about that later, pulls on everything. And the force that it pulls with depends on the strength of gravity at the surface of the Earth and the mass of the object, right? So an object with twice as much mass will have twice as much weight, and weight is the force of gravity. So that's a pulling force. But notice there's something doing the pulling. The Earth is pulling on the cart. And as silly as it may seem, the cart is pulling up on the Earth. Why does it seem silly? Because the Earth is so massive that it holds the cart tightly to the surface. The cart is so small that it doesn't have much effect on the Earth because the mass of the Earth is big. The important point here is this. All forces, all pushes or pulls, are interactions between two objects. Interactions between two objects. In this case, the cart and the Earth. And that is Newton's third law that you're going to learn about this week, usually called action and reaction. I left out the A, that's okay, reaction. And so in most cases it won't be so hard to or weird to think about, but in the force of gravity, the Earth pulls down on objects and those objects pull up on the Earth. The Earth is so big it doesn't have much effect, but that is the action-reaction pair. The Earth pulls on the cart pulls up on the mass. The cart pulls up on the Earth and the Earth pulls down on the cart. That's the action-reaction pair. And the other attribute of Newton's third law, I don't have any room to write it, is those forces are equal and opposite. So the force of the Earth on the cart is mg. Let's calculate it. Okay, I did it for you. So as I said, here just practice. The force, giving it a number, is the mass. So you have to put it in kilograms. As you find out in lab, the mass of those fan carts are about 300 grams. But if you don't change it to kilograms, you're going to get the wrong units, so be careful. 0.3 kilograms times 9.8 gives us 2.94 kilogram meters per second squared. This has a name. These are the units of force. These units are not wrong, they're just cumbersome, so we give it a name called a Newton. Capital N. The force is named after Newton. So that's a force of 2.94 newtons, and so going back to Newton's third law, the Earth pulls down on the cart with that much force, and the cart pulls up on the Earth with the same force. So to the cart, that's a big force because the cart is a small mass, but to the Earth, that's a tiny force. It doesn't have any effect on it. All right, let's look at what about the normal force now? Is that a push or a pull? The normal force is a push. Think about the details now of what happens. You put the cart on the track, And the cart, because gravity's pulling it down, pushes against the track. So if you imagine the track like a spring, it compresses until, it's a very hard surface, but still it compresses until it pushes back with exactly the opposite force, right? If it can't push back with less, otherwise this would keep pushing down. It's not going to push back with more unless it's a spring and it shoots the cart up. So these two forces end up being exactly the same. But they're not action-reaction forces. They're just two opposite forces that happen to be equal because they're in balance and there's no acceleration in the y direction. So you'll see in the lab, the way we write that out, so we write it out this way. We sum up the forces, so go to your diagram. Fn is positive, Fg is negative. In the y direction, notice we're separating the two directions, there is no acceleration, so those two forces are equal to 0, so they have to be equal and opposite, or equal in magnitude to each other. And so the normal force is 2.94 newtons. Now, it's a pushing force, so the track pushes up on the cart, but by Newton's third law, the cart is pushing down on the track, right? So they're pressed against each other. The track is being pushed down by the cart, and the cart is being pushed up by the track. Okay, how about the fan force? Is that a push or a pull? That one's not quite as easy, right? Think about it. The fan force is a push. Remember, all forces are two objects. The cart accelerates, the fan accelerates. What are the two objects? If the fan is being pushed, what's pushing it? You know? Well, the fan spins, and what happens? The fan pushes the air, and the air goes backwards, and the fan and the cart go forward. So the fan pushes against the air pushes back on the fan. That's Newton's third law. And so the faster the fan runs, the more air it pushes. The more air it pushes, the more that the fan and the fan cart are pushed. So we call it the force of the fan, but it's really the force of the air pushing the fan. There is no, since we're ignoring friction and at low velocities any air resistance, that's an unbalanced force. So when we write that equation, we just have the fan force, nothing else, and it is accelerating, and so that's equal to the mass times the acceleration. And so in lab, what do? We'll measure the fan force by measuring the mass of the cart, that's easy, and by measuring the acceleration. That's a kinematics problem, right? We'll let it go 1 meter from rest and measure the distance and use our equations of motion or our kinematics equation to find the acceleration, and that way we find the fan force. Okay, let's go to the next situation. So we can, how is the free body force diagram going to be different in this situation? See if you can fix the free body diagram. What you should do is add one more force. And this, because it's a string pulling something, it's a pulling force, we call it a tension force. So that kind of force we'll call Ft. Just like the track is a normal force, the string is a tension force. And in this case, what you're going to do in lab is you're going to adjust the weight on this, right? If you have too little weight, the cart will pull the weight. If you have too much weight, the weight will pull the cart back. If we get the weight just right, Then we make the tension force, right? We control the tension force by the force of gravity here. And let's just do that. If I drew a free body diagram of the mass, there would be the string going up. That would be the tension force. And then there would be the force of gravity, or M for the hanging mass, times G, down. And so you should be able to visualize that the tension force is going to be controlled by the weight. More weight, more tension. And that's why we use a frictionless pulley, so that the tension force here is equal to the tension force there. And we adjust the weight so that these two forces cancel and we hold the cart stationary. So this equation is still the same, but on this side, what do we get? It changes. I'm going to fix that. Watch. Okay, see if you can follow what I wrote. So in this case, there were two forces. The fan force, positive. I put the negative sign in for the tension force. And they're equal to 0. Why? Because we adjusted this so that the cart is stationary and not accelerating. So those two forces are equal and opposite. So the fan force is equal to the tension force, and the tension force is equal to the mass of the hanging mass. So I wrote it as mh times g. So that's how we get the fan force in method 2. All right, now let's draw the force diagram and think about all the forces acting in this situation. I'm going to pause the video and come back. Okay, notice what I do, because you're going to have to learn how to do this. Since the cart is tilted and it goes along the track, it makes things easier if we put the x-axis here and the y-axis here. So the track is tilted. We also tilt our axes, x and y, to match it. And the fan force, since the cart is tilted, the fan force is along the track. So that's in the x direction. The normal force, remember, is perpendicular. The cart is frictionless. It can roll down the track. The normal force won't push this way, because if the normal force pushed this way, it's kind of pushing the cart up. So the normal force is perpendicular to the surface. It has to be drawn this way. It's easy to make that mistake, and you'll practice this in the Minds on Physics exercises. Gravity, however, is still straight down. The cart's being pulled straight down, and so there is a component of this force. Gravity is doing two things. It's holding the cart on the track in this direction, and it's causing the cart to roll backwards on the track in that direction. And so I'm going to draw those two components. Watch. And I'll draw them with dotted lines because they're not other forces. They're components of the gravity force. I'm making them a little bigger. So what you need to know is that the track angle and this angle are the same angle. I'm not going to go through the trig, but you can see they look to be the same. And so gravity is doing two things. We have to separate out the components, but this angle is not on the x-axis. So this component here is Fg cosine theta, because it's adjacent to the angle. That's the part of gravity holding it on the track, and the force which makes it go down the track is Fg opposite, so sine of theta. Whoops. So let me move it over, and then we're going to do, this is what we have to do. Notice the process. This is what you're learning and need to practice. try and follow. We're going to do sum of the forces. This is how we always start these problems, and we separate, right? We separate the components. Sum of the forces y equals MAY. And so what do you see here? You see Fn minus Fg. The Fg is the mg, so this can also be written as mg cosine theta, right? Because that's how we get gravity. Minus mg cosine theta equals 0, right? There's no acceleration. Actually, there's no acceleration either way. And so if I skip a step of algebra, I get that the normal force up is equal to mg cosine of theta going down. And if I go over here to the x direction, no room. Well, let me squeeze it in. Sum of the forces x equals max. And so that's also 0. So it's going to get messy writing it, but what you can see is that the fan force pushing the cart up, and this part of gravity, right? It's not the whole force, because how much this is going to roll back, the strength of this force depends on the angle. So, right, it makes sense that that force going down the track is Fg sine theta. So the more we tip the track, the bigger the force gets. And so the fan force is equal and opposite to the Fg or mg sine theta. Okay. All right, I'm going to show you one more situation and then we'll stop. So let me get rid of all this stuff. And I'm going to go ahead to next week's lab, where you're going to put a wooden block on the ramp. And you're going to tilt the ramp. You're going to adjust this theta. Right? You can imagine the block is not going to slide down. Why? Okay, that's the other force I want you to think about, because it's a common force that we'll deal with a lot because of the force of friction. And so you're going to tilt the ramp up until the block slides down at a constant speed. Constant speed. Why are we choosing to get it to the point of constant speed? Because at that point, the acceleration is still 0, right? If it slides down at a constant speed, then acceleration along the track, that'll be the x direction, will be 0. Of course, it's not accelerating this way either, so the AY will be 0, so it's a balanced situation. Okay, draw the free body diagram now of this block. Try to do that yourself. Okay, here's what the free body diagram looks like. Notice I tilted the block, and what's holding it up is the friction force. So remember, the normal force is perpendicular to the surface, the friction force is parallel to the surface. So both of these forces are caused by the track. What's different? The cart had wheels and there was no friction. The block doesn't have wheels, so it sticks to the surface with the force of friction. And so notice when you do the lab, you're going to use the same formatting. You're going to see that the block is stationary, so that the y force, which is the y component of the gravity force, has to be equal and opposite these two have to be equal and opposite. And the friction force going up and the force of gravity, the mg, fg, or fg sine theta going down, this force and this force have to be equal and opposite. Why? Because when we do the lab, we have the thing sliding down at a constant speed. And so in both cases, there's no acceleration, and so you have two forces. These two are equal and opposite, and these two are equal. Remember, this is one force, but has two components. So there's three forces, but the y component cancels that, and the x component of the gravity force is in balance or in equilibrium with that, and so there's no acceleration either way. Okay, that's a lot of information, so you may want to do the MOPS, do the assignment, do the lab, and it might be useful to come back and look at this video later after you've actually done some of the Mind Zone physics exercises and done the lab itself.